Hi everyone, welcome to this presentation, which is going to be an introduction to fuzzing. First things first, I want to thank Rajiv for inviting me on TrustX, and I'm really looking forward for all the different video and presentation we're going to see on TrustX Online. So first things first, who am I? My name is Jocelyn Feist. I'm the engineering director of the blockchain team at Trail of Bits. If you don't know us, we are a security company where we specialize in high-end security technology. We work in the blockchain space, and we have been working in the blockchain space for the past 8 years, but we also work in a different field, including traditional application security, cryptography, and so on. One thing that I think differs us from many of our competitors is that we are focused on research, and as a result, we spend a lot of time trying to build tools, and many of our tools are open source. You might know Slither, which is a static analyzer for smart contract, Medusa, which is a smart contract further that we're going to see today, Echidna, Caracal, and so on. But today we are going to focus on a specific technique, which is fuzzing, and we are basically going to try to answer the question on how you can find bugs in the code base, what technique you can use, and what can you apply as a developer or as a security researcher to do so. So if we look at a piece of code like this one, and you want to know if there is some vulnerability, if you want to know if there is some bug there, how can you do that? Spoiler, there is a bug here, but I will let people watching this video to find it. There is basically, on a high level, 4 techniques that you can use to find bugs. First one, unit test. You are going to use basically something like Foundry or Hardart when you are going to create a specific scenario, and you are going to try to see if the program behaves the way you think it's going to behave. Pretty common for software developer. You should use unit tests, and they are definitely useful to find class of bugs, but in practice, they are not going to be that useful to find security-related vulnerability. And the reason for that is that most of the time, when you are going to use unit tests, you're going to use them in a way that are going to help you to test the program in the way where it's supposed to behave, while usually security lies in kind of edge case and non-happy parts of the program. The second class of vulnerability, the second technique to find vulnerability is basically manual analysis. So here is usually when you go through a security company or security researcher, and they are going to go line by line, looking at your code, looking at what your program is doing, and they're going to try to find bugs. This is a powerful kind of approach. You can find a lot of type of bugs, but it is really time consuming. It is also usually costly. There is 2 additional techniques that we're going to see, which are based on tool and on automated analysis. The first one, which I categorize as fully automated analysis. Basically, these are like the tools that you can use out of the box in your code base. There's like 1 or 2 command line to do, and they are going to try to find common vulnerability. You might know Slither, for example, which is a open source static analyzer, which does exactly that. It's going to look at your code base. It knows a couple of known patterns. It's going to rely on static analysis, and it's basically going to try to see if there is one of these known patterns within your code base. For Slither, you can use things like Slither Action, which is a GitHub action, which is going to be integrated within your GitHub, so that every time you do a pull request, every time you do this type of things, you can have Slither running on the go on your development process. The last category, and it's the one we are really going to do a deep dive today, are called semi-automated analysis. So here, you still rely on a tool, you still rely on program analysis, but instead of being kind of like a push-button approach, you need, as a human, you need to provide additional information. You need to have a human in the loop. So it's not the type of tool you can just plug and play and they're going to provide a result. You need to do a bit of manual effort to configure them. For that, there are a couple of subcategories in semi-automated analysis, and we are going today to focus on a specific one, which is called property-based testing, with 2 major tools, Echidna or Medusa. Both of them are developed by Trail of Bits. So the first question you might ask yourself is, what is property-based testing? So that's we need to understand what is fuzzing, because I've mentioned the term a couple of times already today. So what it is. On a really, really high level, fuzzing is just a technique which is going to generate random inputs to your program to stress it. The most basic fuzzer you can think of is if you have an application running, you go on your keyboard and you just push random key within your keyboard just to see how the programs react. Obviously, modern fuzzers are a bit more smarter, and there's a lot of additional technique, but on a high level, that's really the idea. You provide random inputs to the program, and you see how it's going to react. Fuzzing is really well established within the traditional software industry with fuzzer like Eiffel, LibFuzzer, GoFuzz, and so on. These are fuzzers that are used by security researchers in the Web2 space. But for smart contract, we have a specificity that we don't find in traditional software development, is that we are not necessarily looking for traditional vulnerability. I'm saying traditional in the sense that when you are in Web2, for example, when you look at a C or C++ code base, you are going to try to find crashes. You're going to try to find ways to create memory corruption, to create this type of things. We don't have that that often in the smart contract space. And usually what we look for are logic bugs, business logic, arithmetics, access control, but things that are more related to the logic of the program and less about can the program crash. So here, if we just provide random input to the program and see if it's going to crash, it's not going to be that useful. So we are going to use a variation of fuzzing or an adaptation, which is called property-based testing. And here, what we are going to do is that we are going to define so-called invariant or property. Within this talk, I'm going to use invariant and property to say the same things. It's basically something that should be always true within the code base. So we define this invariant, we define this property, and we let the fuzzer generate random input, and we check if this invariant or this property is still true within the code base. A way you can think of property-based testing is really to think of that as unit test on steroid, in the sense that if you have a unit test, you are going to create a specific kind of path and a specific case of your program. Instead of doing one set of inputs to trigger one set of behavior within your code base with unit test, with property-based testing, you basically test thousands, if not millions of them. So it's really a way to create your test on steroids. I've been talking about invariants. On a high level, really an invariant is something that must remain true within your code base. A really basic invariant you can think of is, for example, if you have an ERC20 token and you have a total supply, the user balance of an arbitrary balance should not be above the total supply. For example, if you have a token which has a total supply of 10 million and one of the users has like 20 million, probably something is wrong within the code base, right? Because probably that should never happen. So this is an example of really simple invariant you can define over an ERC20 token. Okay, let's talk about Medusa. So Medusa is our open source smart contract fuzzer that we have been working on for some time now. It's written in Go. If you have experience with Echidna, basically Medusa is our rewrite of Echidna, but in Go. It's really powerful, it's really easy to use, and we have been kind of using all the lessons learned that we have gained through the year building Echidna, and we have built that within Medusa. When you use Medusa, there are a couple of really simple commands you should know about. Medusa init, basically it's going to generate a config file with a default value. This is just going to help you to know what are the different options, what are the different flags you can set. Then you can use Medusa fuzz on the code base. Basically, you start the fuzzing. If you want to learn more about that and all the different kind of configuration, flag, and so on, you can go on securecontract.com/Medusa, which is going to have like all the different options, all the different configuration you can use. But if we think about a really simple example that we were talking about, where we have like a contract and an invariant, how it's going to look like, sorry. Basically, you're going to have your token, Solidity, which is your smart contract. You're going to write invariants in Solidity, which is going to be, in this example, Medusa invariant. You provide that to Medusa, you let Medusa run for a while, and Medusa is going to try to see if it can break the invariant. If we take a really simple example of a token, so this is a token with a transfer function. You can see that to save gas within the transfer function, they use uncheck arithmetic. If you're a bit familiar with arithmetic, you already know that there is a vulnerability here, because if you transfer more value than the balance of the sender, there will be an underflow in the subtraction, which will allow anyone to basically transfer any amount of token within this token. How you can use that? A really kind of like simple pattern to test that is that you're going to inherit from the contract you want to target, which is token here. So you create a test token, which inherit from token. You initialize the total supply to 10,000, and the invariant you are going to test here, the property you're going to test is that no user should have more than 10,000. Really simple, 3 lines of solidity. Here you have an invariant. Yeah, here's the invariant. Now, if you run this with Medusa and you run it with Medusa first, which is a command line, it's going to run for probably 5 seconds, and then it's going to tell you, I found a way to break this invariant, and it's going to tell you, I found it a way to break it, and basically I call a transfer function. I send like a large amount to some address, and if you go back to the code base, you will find out what I've described, that there is an underflow here. The thing which is kind of interesting here and the intuition that I want you to start kind of growing is that here we were building an invariant around the total supply of the token. So our invariant is just about the total supply. And by just doing that, it can now find a bug in the transfer function. So this is really showing one of the kind of important and interesting feature of using Fuzzer, is that you're going to define invariants with respect to some component of your code base. And because the Fuzzer is going to explore all the different functions, it might be able to uncover a bug in a different function from the ones you are trying to test. So as you can imagine, this is really powerful. So now, the question you might ask is how to define good invariant, because total supply balance it's pretty straightforward, right? It's pretty easy, but once we have like more complex code base or like an arbitrary code base for which you don't necessarily know a lot, how you can know if you're going to define good invariant. Here, there is no magic process. There is no like one thing that is going to help you to find all the possible invariants. Through experience, you are going to write sometimes invariants that are good, sometimes that are not so good, and you are basically going to learn as you are kind of gaining experience how to do that efficiently. Recommendation we give usually to people is when you have a new code base, don't try to do something too complex from the beginning. Start with something really small, start with the most straightforward invariant you can think of and you can test, and iterate over it. Don't start by writing the invariant directly in Solidity. Write it in English, then write it in Solidity, run Medusa. If the invariant is broken or if there is like something wrong, you have to investigate manually. If the invariant pass, you can go back and you can kind of like have this iterative process where you define some invariant, you implement them, you test them with a Medusa, and you continue that way. Something you are going to quickly learn probably is that the invariant you might think of might not be true. That's why the step where you need to investigate might take some time, because sometimes you are going to think of an invariant because you believe the behavior of the contract in some way, but in reality it might be a bit more complex. Some example of more or less a generic invariant you can use when you are reviewing different protocol. When you have a math library, there are a couple of invariants that you can use that are usually pretty straightforward. Commutative, 1 plus 2 is equal to 2 plus 1. Identity, inverse. So these are like the basic mathematical invariant you can have. If you have a contract like a token, the first one, the total supply, where the balance of a user should not be above the total supply, is the one we were seeing before. Again, pretty straightforward. Now you can also think about invariant related to specific functionality of the code base. And one example of that is the transfer function. So if you think about the transfer function and you sit down and you're like, okay, what should happen when I execute a transfer? First, your balance, like the user that is calling transfer, his balance should decrease by the amount that you are transferring, and the destination of the transfer should see its balance increase. Right, pretty straightforward. If I transfer 10 token to Bob, my balance should decrease by 10. Bob balance should increase by 10. Nothing magic. Well, the thing is, if you implement that as an invariant, it's actually going to be broken. And the reason for that is that if the destination is yourself, the balance actually stays the same. So this example is just to give you like this insight that sometimes you might think an invariant is straightforward. You might think, okay, like doesn't mean to be tested, or like it's pretty easy. But when you go into like the detail of the behavior and the specification of the function, it might be a bit more tricky, and there are some edge cases to consider. Here in the transfer, transferring to yourself is a specific edge case of the transfer specification. You could also consider reverting and or returning false for function that return a Boolean. Because of that, you will be able to catch maybe behavior that should happen in reverting case, or maybe behavior that you believe should never be triggered with respect to falsification of function. So it's definitely something we also recommend to check. Don't only check for correct behavior on successful transaction, also check for reverting and returns false. There are basically two categories on a high level of invariants. We call them either function level invariant or system level invariant. Function level invariants are invariants that are going to be usually related to a specific function, as the name mentioned, of a contract. For example, the arithmetic invariant that we saw before are related to a specific functionality. Usually, function level invariants are stateless in the sense that they don't involve the state, but it's not always true because you can still have like a state. I mean, you might still like a state variable there. That said, usually they are kind of more contained, and you can kind of target what you're trying to test. The second category of invariant are system level invariant, where basically you try to check a behavior that should be true across any call to the system. So user balance being below the data supply is an example of system level invariant. They are more complex to write, and usually they are also more time consuming, but they might be able to find more kind of deeply rooted vulnerabilities. For function level invariants, usually what you can do, you inherit from the target. For example, if it's a math library, you just inherit from the contract of the library, and you create a couple of functions that targets like the underlying function you want to test. For example, for commutative, and you want to test if addition is commutative, here's how you can write it. You inherit from math, you create the function. You can also use, here we are using the assertion mode, where instead of checking a specific property, we are checking any assertion within the code base. So this also can be also really convenient depending on how you build on the code base. System level invariant are here where, as I mentioned, you want to try something which is a bit more rooted within the code base, or you want to try to fuzz a complex kind of a property of the system. Here, you need usually more complex constructor or setup function. You have like larger harness being like all the code you are writing to set up all the solidity code you are writing to set up the fuzzer. You can use more advanced technique like actor-based fuzzing, which we are going to see in a while. The things to consider here that we don't recommend to start by writing system level invariant. We do recommend to start with function level invariant just because they are easier and they're going to help you to get more familiar with fuzzing and get more familiar with the code base. Here, if you do that, the user is going to explore all the other functions as I mentioned. So it's really kind of like almost a simulation of a full blockchain where you can have multiple contracts, multiple interaction, and so on. So this can be really, really powerful. So a couple of tips that you should consider when you want to write fuzzing harness for complex code base. A common mistake we have seen some people do when they start fuzzing is that they want to go straight away into the implementation of the invariants. And when they do that, once you start having complex fuzzing harness, when you start having complex kind of like a code base, it is difficult to do it that way. What we recommend is really to think about the design of your harness, the design of the invariants before even implementing it. There are a couple of questions you might ask yourself. For example, do you want free or guided exploration? This means that, for example, once you want to explore a specific function with a fuzzer, you might write preconditions. So, for example, if you want to bound the parameter to some value, for example, in the transfer of amount, maybe you want to have the fuzzer exploring only transfer between 1 million and 10 million, or if you want to do a swap, do you want maybe like to have some limit in the amount of swap, or if you have like a system with a fee, maybe you want to guide the fee to be within some boundary. This is important because if you think about that before implementing your harness, you might have different architecture, long versus short run. So depending on your resource and depending on the time you have to do the fuzzing, you also need to think about if you want a long run or short run. Long run might be something where you want to fuzz the code base for like 3 weeks, 4 weeks, and then you can have like some harness that are going to be really large and really complex. While if you just have 1 week to do invariant development, maybe you should focus on short run. And if you focus on short run, you know that the code base might not be fully explored, so you won't be able to kind of target like complex interaction. In that sense, you probably want to focus a bit more on function level invariant. The last one, rank versus actor-based fuzzing. I have an example of actor-based fuzzing in the next slide. But basically, once you want to start to simulate multiple interactions within the system, you have usually two approaches. Either you use VM-Prank, which is a cheat code from Foundry and supported by Medusa and Echidna. Basically, it allows you to prank, so to change the color of an internal call. If you do that, it might become complex to set up your fuzzing. It might be complex to find out what are the different actors, what are the different addresses that interact with your system. You can use a different approach, which is actor-based fuzzing, as we're going to see in a bit. The TLD of what I kind of want you to remember from here is that from the moment you're going to build a complex fuzzing harness, it's almost more about software development and security. It's really about design. It's really about how you think about how you're going to write your code in the long term. And this is important in particular if you want to fuzz something really complex, you really need to sit down and think about the design. As I mentioned, there is this strategy of using actor-based fuzzing. Basically, what it means is that every actor of your system is going to have your own contract. For example, if you have a system where you can have liquidity provider and users are going to swap asset, you are going to create a liquidity provider contract, you are going to create a swap contract, and you are going to implement the internal logic of how this user, this actor, is going to interact with the system. Then you might have an orchestra contract, which is going to take the different actor, mix and match and create different scenario, and all of that using fuzzing. So all of that is going to become randomly assigned, and they're going to mix and match like the different actors, the different action in a random fashion. And this is going to be really, really powerful if you want to create a fuzzing harness for complex contract, which has multiple contract interaction. A good example of that can be found in Uniswap v4. So during the Uniswap v4 audit, at Bit, we ended up writing an actor-based stateful fuzzing harness for Uniswap v4. You will find the report in this QR code or on this link, and you will find the invariants which are public on GitHub. But basically, here the idea is that we have an entry point, which is going to be the orchestra I mentioned. We are going to have different actors that are singular contracts, which are going to provide different action, swapping, adding liquidity, and so on. And all of that is going to be given to Medusa or Echidna, and it's going to allow the fuzzer to explore really complex interaction within the protocol and then check the invariant. So this allowed us to really do a large exploration of different behavior over Uniswap, which is not like the simplest code base because you have a hook system, you have callbacks, you have all of that. And this approach of state-based, of actor-based fuzzing did allow us to do that. I highly recommend to look at our report, which gives more detail about our approach and the invariant, which are public. In my opinion, the Uniswap v4 fuzzing is one of the state-of-the-art of what you can find in fuzzing on complex system for smart contract. Okay, there are other fuzzer that exist. Probably like the most common one and the one you might be familiar is the one in Foundry. The fuzzer in Foundry is really nice for simple test. If you want to quickly test something which already use a Foundry code base. However, from our experience, the fuzzer is just not as powerful as what we have built. We have been building fuzzer for more than a decade now. Echidna is probably 6 or 7 years old. So we have really spent many kind of years fine-tuning our fuzzer to be really efficient because we have been using them in almost all our audit over the past 6 or 7 years. So really, while Foundry might be easier for simple tests, from the moment you want to try complex fuzzing and you want to try kind of real-world invariant, I highly recommend to check out Medusa. Echidna, which is our previous fuzzer, is basically the previous generation of Medusa. We have been rewriting Echidna with Medusa. Historically, Echidna has been written in Haskell. Medusa is written in Go, so it has allowed us to kind of develop, faster, like the further. And we have also used all the lessons learned we have kind of gained through the year with Echidna, and we are applying them in Medusa. So we are really excited to see the new result of that. In the realm of semi-automated analysis, when you have a tool and you provide a specification or an invariant, there is a different category of techniques you can use, which are basically based on formal method. You might know KVM, Certora, Almos, for example. The idea of this technique is that instead of executing the program with random transaction and random input, they are going to create mathematical representation of the code base, and they are going to check if the mathematical representation works within the variant you want to do. This is really powerful because now you can have a proof because it's a mathematical representation. However, in practice, this technique, they are more difficult to use. And if you have like a limited amount of time, the return on investment is just lower than fuzzing. At Bit, we have been using both approach. We have been using formal method and fuzzing. And in practice, fuzzing is just a better return on investment. That said, formal method might be useful if you have a large amount of resource. If you have if you can spend like 6 months to test invariant, that might be useful. Or if you have really specific piece of code for which you want really a high guarantee, for example, arithmetic library might be a good target. That said, I highly recommend to start with fuzzing. I don't think there is a need to use formal method if you don't have already a good fuzzing harness. So start with fuzzing. If you want to go to the next step, you might consider formal method. Okay, if you want to learn more about everything I just mentioned today, you can go on securecontract.com. It has a couple of exercises, and it has more detail about fuzzing and how to use the different tools. We have a repository which is called properties, which contain basically a set of properties that can be applied in generic code base. For example, if you have an NFT or an ERC 7021, we already have pre-built invariant that you can just plug and play within your system. So high-level thing that I want you to remember from this is that if you want to start with invariant, start simple. Start in English, then Solidity, then iterate. Don't try something too fancy. Don't try something too complex. If you find a bug with your first invariant, probably there is something going wrong either in the code base or in your approach. I highly recommend you to try Medusa on your current or next project, because the more you kind of get exposure and the more you get experience to fuzzing, the easier it's going to get for you to be quicker. If you are a software developer and you want help to use this different tool, we have a specific services at Bit, which is called Invariant as Services. Basically, our idea is that here we work with our clients to help them to build fuzzing harness, to help them to speed up their understanding on how to build a fuzzer. And our end goal is for fuzzing to be integrated within the development lifecycle of our clients. So that's how we are trying to do that. We do a lot of teaching, we do a lot of invariant kind of discovery with our client, and we also write them and configure the fuzzer for them. So if you're interested, you can find out the link here. And thank you for your attention, and I hope that was useful for you today.